Let's start off with a warm-up about an SAT question. It says the denominator of a certain fraction is 9 more than its numerator. If the fraction is equal to 2/5, what is the denominator of this fraction? What I want you to do now is I want you to stop the video, see if you can work it, and then rejoin us and we'll go over the solution. All right, welcome back. It says the denominator of a certain fraction is 9 more than its numerator. Well, do I know the numerator? No. So if I don't know the numerator, I give it an x. Well, if the numerator is x, how do I express the denominator? It's 9 more than the numerator, and the numerator is x. So 9 more than implies addition. And the fraction is equal to 2/5. So we set those two equal to each other. Now this is a proportion that all we have to do is solve. So what I'm going to do is, now I do this every time so I don't make a distribution mistake. I always put a binomial or more in parentheses. So anytime I see a binomial in a fraction in which I'm going to have to cross multiply, I always put it in parentheses. Now I cross multiply. 5 times x is x. And 2 times x plus 9 becomes 2x plus 18. Now I simply solve like a two-step equation. I subtract 2x from both sides and I get 3x. 3x equals 18, so I divide by 3 and I get x is 6. But it didn't ask me what x is, it asked me what is the denominator. Okay, so I know the numerator, it's 6. So I plug 6 into the denominator. And 6 plus 9 is 15. All right, let's go to the next one. All right, let's review how we factor a GCF. Now, you're not going to be doing any factoring in this unit, but what we're taking advantage of in this unit is we are going to be reviewing our factoring skills so that way, when we get involved in Unit 4, you've already reviewed your Algebra 1 factoring skills and you're ready to move on to more challenging problems. So we're going to start off by factoring a GCF today. So what you can do, there's a couple of different ways that you can go about getting your greatest common factor. One way is you can expand out the multiplication. Now, if you look here, we have 3 terms. You can view them as terms or in a box, either way, but we have 3 terms. Now, if I expand out the multiplication, I like to expand it out to the product of a prime and another number. So if you were to ask yourself, what's the biggest number that divides into 20, 12, and 8? You would say 4, because 4 is the biggest number that goes evenly into 20, 12, and 8. And if you look here, 4 appears in both, not both, but all 3 terms. All right, the next thing, when you're factoring out a variable GCF, you can only factor a variable out if all the terms have that variable. So if you look at the first 2 terms, they all have a y. But if you look at the third term, it doesn't have a y. So since that third term does not contain a y, I cannot factor a y out. So I pick, when I'm choosing variables, I always pick the variable that has the smallest exponent, because you cannot factor an x to the 4th out of an x cubed, because x cubed is x times x times x, and x to the 4th is x times x times x times x. So in the first one, there's not 4 x's, so you always pick the variable that has the smallest number. So let's revisit that. When you are factoring out a numeric GCF, you pick the biggest number that goes in each term evenly. And when you're picking a variable GCF, first of all, it must be contained in all the terms, and then you pick the variable with the smallest exponent. So looking at this problem, I know 4 is the biggest number that goes into 20, 12, and 8. The smallest x I have is x cubed. They don't all three have a y, so I can't pull a y out. And then the smallest exponent on the z is a z squared. So my GCF is 4x cubed z squared. Now I have to put what's left in each box. So you can look at this one of two ways. You can say what times 4 gives me 20, in which case it's 5. And if I pull 3 x's, like an x cubed, out of an x cubed, what am I left with? So I crossed out the factors of my GCF, and then I can see what I'm left with. I am left with 5y squared z cubed. Now if I look at the second term, 4 times 3 is 12. If I pull 3 x's and out of 5, I have 2 left over. I have the y because I didn't factor out the y. And if I pull a z squared out of a z squared, it goes away. So we are left with 3x squared y to the first. Now you may ask, is it necessary for me to put that one exponent on the y? And the answer is no. So if you'd rather put y to the first, that is perfectly acceptable, or you can just say y. That's a personal preference. All right, same with 8. 4 goes into 8 2 times. If I pull x cubed out of x to the fourth, I have 1x left, and z squared out of z cubed gives me 1z. So, again, could I put just x times z? Absolutely. So, when I'm writing this problem, and I'm writing the factor form, 4x cubed z squared, and then I write what's left, 5y squared z cubed plus 3x squared y minus 2xz. And then I close the parentheses. Now, you can always check your work by redistributing and see if you get back the original problem. If you get back the original problem, you know you have factored correctly. All right, so this is what we are left with. Let's move on. Now, here's 3 that I want you to try on your own. So what I want you to do is pause the video and try these 3, and then restart it when you're ready, and you can check your work. All right, let's start back up. That's what I get for factored form of the first one, the second one, and the third one. How did you do? All right, let's move on. These are just some thoughts to start your day, kind of some fun, some serious, but especially in this time, this quote is so applicable. So just know that you are doing your best. Look at how far we've come. Did we think we'd be here in March? Probably not. But it says, look how strong and resilient you are. No current situation or challenge can hold you down. You are too powerful. Snap out of the overthinking. Remember who you are, why you started, and where you're headed. All right, so let's go ahead and let's get started with our notes. As you're aware, we are starting a brand new unit with these notes. Unit 2. Unit 2 is all about the systems of equations. So in notes 2.1, we are going to focus on solving systems of equations in 2 variables by graphing, substitution, and elimination. We are going to visit all 3 types, just like we did in Algebra 1. Let's start by reviewing how we solve a system by graphing. So my system of equations is 2x plus 4y equals 12. and then y equals negative x plus 2. Now, first of all, before I start this, when you have an equation in standard form, if you're more comfortable by putting it in slope-intercept form and graphing it that way, go for it. I'm not going to dictate how you have to graph these lines. I'm going to tell you, if I was looking at this equation, what route I might take. But again, if you're more comfortable putting it in slope-intercept form and graphing it that way, that's all that matters. All right? So we're going to start with our first equation. It's 2x plus 4y equals 12. So when I have an equation in standard form, I always use the x and y intercepts to graph. So I'm going to start off with the x-intercept. That means y becomes 0. Well, anything times 0 is 0, so I end up with 2x equals 12, which means x equals 6. So my x-intercept is 6, 0. Now for the y-intercept. For the y-intercept, I'm going to put x as 0. So that gives me 4y equals 12, y equals 3, which means my y-intercept is 0, 3. So now I connect the dots, and there's my line. Now, the second line is already in slope-intercept form. So I have a y-intercept of 0, 2, and I have a slope of negative 1. So I'm going to start at 0, 2, and then I'm going to apply my slope of down 1 over 1. Now, if I continue down this direction, the lines are not going to intersect. They're going to keep getting further apart. But if I go back up to 0, 2, and instead of going down 1 over 1, going up 1, left 1, let's see what happens. Up 1, left 1, oh, I think we're going to intersect. Up 1, left 1. So I can tell that my two lines intersect at that point. Now remember, the solution to a system of equations, regardless of if you graph it, solve it by substitution, or solve it by elimination, the solution to a system is always a coordinate point. It is a place where the two lines intersect. Okay, so always remember your solution is a coordinate point. So I look here and I see that those lines intersect at negative 2, 4. So negative 2, 4 is my solution. Now, here's the point I always like to make. Y'all should always get a 100 on your homework, quizzes, and tests when it comes to solving a system of equations. And the reason for that is you can always check your answers. You should always plug your answers into both equations. And if that coordinate point makes both equations true, then you know you have the right answer. If it only makes one of them true but not the other one, you've made a boo-boo somewhere and you need to go back up there and fix it and find it. So let's check our answers. 2 times negative 2 is negative 4. 4 times 4 is 16. So negative 4 plus 16 is 12. But just because it makes one true doesn't mean it makes both true. So let's go in and try the next one. Negative x, so that's negative negative 2, which is positive 2. 2 plus 2 is 4. Okay, so that coordinate point makes both equations true, so we know we've gotten it right. All right, let's look at solving by substitution. Substitution is when you solve one equation for a variable and you use that solution to represent that other variable in another equation. So take, for example, we have 4x plus 2y equals 7. And then my second equation is y equals 5x. So since y equals 5x, I can take this y in the first equation and substitute 5x in its place. So that becomes 4x plus 2 times 5x equals 7. Well, 2 times 5x is 10x. And now I combine like terms. 14x equals 7. I divide by 14, and that becomes 1/2. Well, now that I've got x, I need to find y. It really does not matter which equation you pick to plug back into. You could take x equals 1/2 and plug it back into the top equation and solve for y. Or you could look at the second equation. The second equation is already solved for y, so I am going to sub in 1/2 for x. So 5 times 1/2 is 5/2. So my solution is 1/2 5/2. Now, unless the directions tell you, you don't need to change that to a variable. Leave it as a fraction. But just like with graphing, we want to check our answers. So I'm going to come up to the top equation, 4 times 1/2 plus 2 times 5/2. And we want to know, does that equal 7? So 4 times 1/2 is 2. 2 times 5/2, well, that's 10/2, which is 5. And indeed, it does equal 7. So it works in that one. Now, granted, we use the second equation to get our answer, our solution for y, but for grins and giggles, let's just check it out. So my y is 5/2, and that's 5 times 1/2. And that indeed makes a true statement. So it makes both equations true. So we know that our solution is 1/2 5/2. Okay, let's have you try a substitution problem on your own. Let's have you pause the video and then restart it when you're ready to see the solution. All right, welcome back. What this says is I have 4p plus 2q equals 8, and then q equals 2p plus 1. So what that means is I'm going to take that q and I'm going to replace it for 2p plus 1. I now distribute the 2, combine like terms, and move the 2 to the other side, subtracting 2 from both sides. I then divide, but 6 over 8 is 3/4. Well, I've got the value for p, now I need to get the value for q. So I substitute into 2p plus 1. Could I have plugged it in the top one? Absolutely. But the bottom one is already solved for q. So I just have to plug in and simplify. So I plug in 3/4 for p, and then I solve. And I get 3/4, 5/2. Now you may be wondering, how do you know if it's not x and y? How do you know what variable to write first? Well, if they don't tell us that something's a function of something else, so we don't know the independent and dependent variable, if we don't know any of that information, we always put our coordinate points in alphabetical form, in which case p comes before q. Now, you may be wondering, well, how did you get 5/2 out of that? Well, let's review that. So I've got 2 times 3/4 plus 1. Well, that's 2 over 1, which is 6 over 4. 6 over 4 reduces to 3/2. And getting a common denominator with 1, well, that's 2. So 1 is equivalent to 2 over 2, which explains how I got 5/2. So, as always, we want to check our answer. All right. Well, we already know if we plug in 3/4, we get 5/2. So that equation works. Now, let's try the top equation. So the top equation I'm going to erase my scratch work up here so that I have room to plug it into the top equation. And so I get 4 times p, which p is 3/4, plus 2 times q, which q is 5/2, and altogether that's supposed to equal 8. Well, the 4's cancel, so I get 3. The 2's cancel, so I get 5. And indeed, 3 plus 5 equals 8. So it works in both equations, so I know I've got the correct solution. All right, let's look at an application problem. So first of all, we're going to write a system and then we're going to solve it. And cost is a function of transactions. So cost is going to be equivalent to the y value and transactions is going to be equivalent to the x value. So the scenario tells us that Bank of Money charges 50 cents per transaction and no monthly fee. And then Low Fee Credit Union charges a monthly fee of $12 and 15 cents per transaction. So what we're going to do is we're going to set up a system and we're going to look at when will the cost be the same. So let's start with Bank of Money. Bank of Money does not charge you a monthly fee. Okay, so we're just going to do the system for 1 month. So looking at a 1 month charge, they are not charging me for hanging on to my money. The only thing they're going to charge me is 50 cents per transaction. So the cost for Bank of Money is simply 0.5 times the number of transactions. Could I have put 0.50? Absolutely. But I just shortened it and made it. So the cost for Bank of Money is 0.5 times the number of transactions. Now, let's look at low fee credit union. Okay, so low fee credit union, they're charging me a monthly fee of $12. So regardless of if I have any transactions or not, they're still going to charge me $12. And then on top of that, they're going to charge me 15 cents per transaction. So my equation looks like that. 15 cents for each transaction plus that $12 monthly fee, regardless of if I have to use, if I make any transactions at all. So $12 flat fee and then 15 cents per transaction on top of that. Now, if I graph both those equations, I see that they intersect right there. And you're like, holy Toledo, Batman, that didn't fall at a pretty place. But I want to know when the cost will be the same. So I want to know when the cost for Bank of Money will equal the cost for low fee credit union. So I want to know when cost equals cost. So I can set both equations equal to each other. I bring 0.15t over and I get 0.35t equals 12 divided by 0.35 and I get about 34.286 transactions. So we're roughly going to say that approximately at 34 transactions, the cost for either bank will be the same. So if you make 34 transactions a month, hot diggity dog, it doesn't matter which equation you use. However, so that's when the cost will be the same. But what if I want to know who would you use if you made less than 34 transactions and why? So if I make less than 34 transactions, that means going to the left of that intersection point, I'm gonna pick that bank, because if the line represents the cost, this line for cost is most definitely lower than the one above it. Well, this line is Bank of Money. So I would use Bank of Money because for less than 34 transactions a month, they've got the lower cost. However, who would you use if you made more than 34 transactions and why? Well, going in terms of greater than 34 transactions would be to the left of the point, which would make it this line. Well, if you trace this line all the way back, you're going to see that it's low fee credit union. So if you make more than 34 transactions a month, you're going to want to go with low fee credit union because the cost is lower. Let's talk about how we solve by elimination now. Now, for you to use elimination, it has to meet some criteria. First of all, x and y, or your two variables, need to be on the same side. That's the first criteria. The second criteria is, for example, if you want x's to eliminate, then, for example, one x needs to be 5x, and the other x needs to be negative 5x. So they need to have the same number, but opposite sides, in order for that variable to drop out. So let's look at this example. We have 3x plus 2y equals 6, And then we have 1/3 x plus 1/3 equals y over 9. Now, in the first equation, it's got x and y on the same side. But in the second equation, it doesn't. So my first step is to get x and y on the same side. So I'm going to subtract y over 9 from both sides, and I'm also going to subtract 1/3 from both sides so that it resembles this equation. You'll see that I now have 1/3 x minus y over 9 equals negative 1/3. Okay, I don't want to be dealing with fractions. Yuck. So in that second equation, I'm going to get those denominators to cancel out. So I'm going to clear some fractions. Okay, so looking at the denominators, I have a 3 and a 9. Well, the least common denominator is 9. So I'm going to multiply both sides of the equation by 9. Well, 9 times 1/3 is 3. The 9's cancel in the second term. And in the third term, I get negative 3. So when I take this 9 and distribute it, 9 times 1/3 is 3. 9 times y over 9 is y. And then 9 times 1/3 is negative 3. So now I've got x and y on the same side. I don't have to deal with fractions. And now I get to decide what variable to drop out. Now, I'm going to tell you this. It doesn't matter which variable you choose. For example, if you looked and you said, I have a 2y here and it's positive. If I could make this a negative 2y, my y's would cancel. So I'm going to multiply the second equation, everything by 2. So that way I'd have 6x minus 2y equals negative 6. Awesome. Or if you saw and you were like, well, I see that I have a 3x on top and a 3x on bottom. If I multiplied that whole bottom equation by -1, the x's would drop out. And you'd be correct in doing it that way. So again, one person may get rid of the y's, one person may get rid of the x's, but as long as their math is sound and the work is correct, you're going to both arrive at the same solution. So what I'm going to do is I'm going to multiply the bottom equation by -1 because I chose to get my x's to cancel out. So that gives me 3x plus 2y equals 6. And then the bottom equation becomes negative 3x plus y equals positive 3. I'm now ready to add down the columns. Sweet, my x's cancel out and I get 3y equals 9. I then divide by 3 and I get y equals 3. Woohoo! But I'm not done because remember what we said in graphing. The solution to a system of equations is a coordinate point. It's a place where those two lines would intersect. So I've got the y, but I still need to know what the x value is. Now, does it matter which equation I plug it back into to get the x value? The answer is no. It really doesn't matter. I'm going to pick the top one. So I substitute in 3 for y. And I get 3x, and then 2 times 3 is 6, so 3x plus 6 equals 6. I divide by 6, and I get 3x equals 0, therefore x equals 0. So my coordinate point is 0, 3. But we still want to check and make sure that it works in both equations. So let's plug 0, 3 back into the top equation. So I have 3 times 0 plus 2 times 3 equals 6. Well, that goes to 0, and 2 times 3 definitely equals 6, so we're good there. Let's try the other one. 1/3 times 0 plus 1/3 equals 3 over 9. Well, that definitely goes to 0, and 1/3 is the equivalent of 3/9, so it works as well. So we've got the right solution. Okay, let's look at another solving by elimination problem. We have 2x minus 3y equals -1, and we have 3x plus 4y equals 8. X's and y's are on the same side. There are no fractions, so now we can jump ahead to which variable do we want to drop out? Now, I'm going to be totally honest. It doesn't matter which variable you choose. You can get the x's to drop out, or you can get the y's to drop out. It doesn't matter. I'm looking though, and I'm seeing that we have a positive y on bottom and a negative y on top. So the signs are already opposite. So all I have to do is manipulate the numbers in front of them, and then the y's will drop out. So I think that's what I'm going to choose first. Now when you do this, this is not where you just have to multiply one equation and then boom, things cancel out. So what I'm going to have to do is I'm going to multiply the top equation by 4, and I'm going to multiply the bottom equation by 3. Now you may be wondering why not negative 3? Because negative 3 would flip them into having the same sign in front. So we don't want that. So we're going to multiply the top equation by 4, everything on top by 4, and then we're going to multiply the bottom equation by 3, everything by 3. Now, if you notice, the y's cancel, and we're left with 17x equals 20. We divide by 17, and x is 20 over 17. Now, we have to plug back into one equation, doesn't matter which one you pick, and we have to solve for y. I'm going to pick the bottom equation. So I plug in 20 over 17 for x, and that gets me 60 over 17 plus 4y equals 8. Gross. I don't want to deal with a fraction. So I'm going to multiply both sides by 17 to clear the fraction to make it a little bit better to solve. So that gets me 60 plus 68y equals 136. I subtract 60, divide by 68, and I get 19 over 17. So my solution is 20 over 17, comma, 19 over 17. Now, of course, you'll want to go back in and check your answers. If you're asking for my opinion, I'd check this one on the calculator. Just make sure, though, that you put your fractions in parentheses so your calculator treats it like a fraction. Now, let's say, hypothetically, that we instead wanted the x's to cancel out. So I'm kind of rewriting the system. So let's say, again, in this case, I want the x's to cancel out instead. So what I'm going to do here is I'm going to multiply the top equation by 3 and the bottom equation by 2. Now, here's the thing, though. They're still going to be the same sign. So you have to make one of them a negative multiplier. Does it matter which one? Nope. So I'm going to make, I'm going to make 2 the negative. So again, multiply that by negative 2. And again, this time you're getting the x's to drop out, so you get 19 over 17 first, then you'd plug 19 over 17 back into one of the equations and solve for x. So that's basically the only difference. So if you're trying to eliminate a variable in which the signs are the same, you want to make one of the multipliers negative. That way you get a positive and a negative. Okay, let's look at what happens if the variables add out when solving by substitution or elimination. Well, you're either going to have no solution or infinitely many solutions. So let's look and decide with this example, how do we determine which one is which? So I have 2p plus 3 equals z and 2p plus 4 equals z. Well, if they both equal z, they equal each other. Transitive property. So we have 2p plus 3 equals 2p plus 4. So I need to get the p's on the same side. But if I subtract 2p from both sides, they both cancel out. And I'm left with 3 equals 4. Now, is that a true statement? Will 3 ever equal 4? The answer is nope. So we consider that a false statement. So if you get a situation where the variables add out and then what's left is a false mathematical statement, you know there's no solution. And when there's no solution, that means that you have parallel lines. Those lines will never intersect. So if you get a false mathematical statement, you know there's no solution to the system, and therefore your lines are parallel. Now, let's talk about this. What if I get something like a true statement? So if I get 4 equals 4. So again, this wouldn't be the solution to this one, obviously, but if I result in my variables dropping out and I get a true mathematical statement like 4 equals 4, if that happens, then I know there's infinitely many solutions. And what that also means is that these two lines are the same line. So same line, infinitely many solutions. All right, let's look and see how we classify and draw a graph representing two linear equations with one solution, no solution, or infinitely many solutions. So if we have one solution, that means our two lines intersect in only one place. If we have no solution, that means our lines will never intersect, therefore they're parallel. And then infinitely many solutions means that our two lines are the same line. So how do we classify a system with only one solution? If we have a system that has only one solution, we classify that as independent. If we have no solution, meaning our lines are parallel, that means your system is inconsistent. And then if we have a system of equations where we have infinitely many solutions, meaning my lines are the same line, we call that system dependent. All right, let's look at the last slide. This is a challenge question. We want you to analyze the following systems of equations and choose a method. Don't solve it, but just choose what would be the best approach to solving this system. We want you to explain why you chose that method that you did and support your decision with at least one reason. So pause the video, answer the question, which method would you choose and why, and then hit play again to see what we would say. Okay, for the first system, I would choose elimination because x and y are already on the same side. For the second system, I would choose substitution because the top equation is solved for one variable. It's already solved for x, so we can plug that into the second equation. For the third system, you could choose graphing because both equations are in slope-intercept form. Or you could also choose substitution because both equations equal y and therefore equal each other, aka the transitive property. If A equals B and B equals C, then A equals C. And that's it. Your homework is to go and complete worksheet 2.1, and then you're done. Don't forget to check your answers and submit it back to the teacher. Have a good one.